you everyone for joining this tech talk. It's the first one of two that Megan Hine from Dräger has kindly offered to present to our members around hydrogen, and we're going to do, what's the second one, Megan, remind me?
Carbon dioxide.
Carbon dioxide, yeah. So we've kind of got like a renewable energy flavour. So yeah, so over to you, Megan.
No worries. Right. Thanks ever so much for having me. Hopefully for the majority of you, Dräger needs no introduction. I'm not going to go into like company profile and everything like that because we're a little bit tight on time and it's quite a big subject. So I can actually click that forward. Yes. Right, we're going to talk in the first subject here about hydrogen safety. I'm going to try and cover in an impartial way just the way that the gas behaves, what options are available to you from a technology perspective, technically. Obviously, we will cover some Dräger products, but I'll also mention some other products that are out on the market as well. All of them are very good. You know, no one's out there really making a bad gas detector, not when you're sort of paying for a good industrial brand, which I'm sure many of you are aware of. So hopefully you'll kind of go away from this with a better understanding of hydrogen overall. So we've just got some facts to kind of go through, but I am going to compare hydrogen throughout to methane because that's kind of the gas that you guys are probably most used to working with from an energy perspective. And there are some important differences and it's quite easy to relate. So hydrogen is 14 times lighter than air. It is the lightest molecule. People are fond of kind of saying, oh, it's the most abundant molecule in the universe, which it is, but it's not the most abundant molecule on Earth. We have to manufacture it. And so that means that we have a little bit of an energy penalty when it comes to using hydrogen by comparison to natural gas or methane, which is, of course, over millions of years has come to exist in subsea storage or underground storage locations, and we can basically just extract that without having to manufacture anything as such. Methane, of course, is also lighter than air, but not as light as hydrogen. It has an ignition energy that's an order of magnitude lower than methane, so it's 0.019 microjoules, whereas for methane it's 0.1, and that means that the size of spark required to ignite a release of hydrogen is significantly an order of magnitude smaller. I think there's a fact that if the static electricity discharge that you get when you rub a balloon on your clothes and then you can feel the spark, that's 0.01, and hydrogen here has an ignition energy of 0.02 essentially. So that it kind of gives you some context in terms of the size of spark required. So static electricity discharge is going to be a massive consideration when designing process plants for hydrogen. That's not the business I'm in. I'm only ever in the business of what if it leaks, but it's just something to take into consideration. The molecule size is a quarter of the size of that of methane, which has led some people to speculate, mainly on the internet, about the potential of hydrogen to leak where methane doesn't. And generally, I would say in almost all circumstances, I can't think of one where it has been proved otherwise, a system, if it is leak tight for methane, will be leak tight for hydrogen. The DMV future grid project that's going on up at Spade Adam, where they've taken sort of 25 and 30-year-old pieces of pipe work from the national grid, compressors that have been in use for a good number of years or decades, coming to the end of their life. They've created this grid out of old pieces of infrastructure to try and give some prediction of how the infrastructure will behave once we get to that kind of age and putting methane, hydrogen through it. And what they found is that if it's leak tight for methane, it's leak tight for hydrogen, and there are a number of other studies that have suggested that as well. One of the things to take into consideration, there is some research that suggests that hydrogen doesn't leak any faster than methane when you do have a leak at low pressures, but that does change when you're operating at high pressures. And the research suggests that at higher pressures, hydrogen can have a propensity to leak at 10 times the rate of methane. So both of them will be leaking, but that the molecule of hydrogen will escape more readily if there is a leak. And that is partially to do with the viscosity of hydrogen as well as the molecular size. It has a really low viscosity, so it just means that it moves really, really freely. And we see that in how easily it diffuses as well once the gas has escaped, which isn't necessarily a good or a bad thing. The explosion velocity of hydrogen is 7 times higher than gasoline and methane. So if you do get an explosive gas cloud buildup and that gas cloud ignites, the explosion wave will travel much faster. I think it's 3.51 meters per second as opposed to, I'm not even going to guess, it's on another slide. It's, I think, under 1 meter per second for methane, but my memory's failing me. Hydrogen has a lower explosive limit of 4% volume in air, which isn't that dissimilar than methane, which according to the European regulations is 4.4% volume in air. For American regulations, it is 5%. So the lower explosive limit is not that much change, but the upper explosive limit is significantly different. I recall from memory, I believe I don't deal with upper explosive limits so much, but I think methane is 16.4. Hydrogen is 75% volume in air. And what does that even mean? Like, why is that important? So for that, we really need to think about the fire triangle. So this is a universal truth. In order for there to be a fire or any kind of explosion, you need the fuel, which is the hydrogen or methane in this case. You need the oxygen present in the air, and you need heat or an ignition source. And we've already talked about the fact that the ignition source for hydrogen can be significantly smaller and still be able to ignite that gas. And if you remove any one of those things, you won't get a fire, essentially. And what we're talking about here with the upper explosive limit is the removal of oxygen. So you can get to the point where you get too much of the fuel that actually displaces the oxygen and means that you've no longer got the ability to have an explosive atmosphere because there's not enough oxygen to support combustion. Now, for methane, that window is roughly 10% volume in air, maybe a bit more, 12. Whereas for hydrogen, you can see it's 71% volume in air is the window at which it remains explosive. So you don't really want to rely on there being too much hydrogen presence in order for there to prevent an explosion. Not that you would ever take that as a strategy in general, but it's just a much bigger explosive window. Hydrogen is odorless, as is methane. A lot of the public think that methane has a smell, but of course that isn't the odorant that we inject into our domestic natural gas pipelines in order for our nose to behave as a gas detector. And interestingly, I think NGN and SGN with their hydrogen for homes trials are putting odorants into their process to enable this to continue. The public is used to being able to smell a gas release. There was some concern about the fact that obviously with the first fact, with hydrogen being so much lighter than air, of course, and being the lightest molecule, that no odorant would be able to follow the hydrogen molecule. So you wouldn't get necessarily the smell ending up where the actual gas explosion potential was. However, if you're a human being intending to use your nose as a gas detector, you actually don't want the smell to be lingering up at 8 foot in the air at the height of the ceiling. You need it where at the breathing area for human beings. So I think the strategy was taken that not only does the odorant still prove useful, but also that it can add some color to a flame when burned in a domestic environment as well. If you've been to the NGN hydrogen homes trial over at Thornley Lane, and it is publicly available to be open, so it's quite a good trip if you organize something like that, maybe put a bus on or whatever. But they've got these homes that are a hydrogen boiler, hydrogen hob. We've got gas detection in there as Dräger. We don't normally do domestic gas detection, and it's a long story as to why we do have it in there. But I've seen the hob working, and they're not using odorant there, but you can just about see the flame because of the way that they've designed the burner. But when they do put odorant in there, eventually you will be able to see the flame even better. But in a process environment, pure hydrogen burns with an almost invisible flame. So at night, you can just about see it. It gives off a lot of light in the infrared and ultraviolet range, but of course our eyes can't see that. And there's minimal light given off in the visual range for human beings. So essentially, it is invisible, especially during daylight. The other thing to know is that hydrogen fires have a low radiant heat, which means that you can get your hand quite close to the flame before you actually start to feel any heat. That is because of the low carbon content. It's actually the carbon in a, say, like a hydrocarbon flame or a carbon-based fuel flame that gives off that amount of heat for us. So not only can you not see it, but you can actually get really close to it before you would ever start to feel its effects as well. Dräger have been detecting hydrogen gas for a long time in a number of different industries. One of the most common industries for this is where it's used as a feedstock in the manufacture of ammonia as part of the fertilizer industry. So we have both carbon monoxide and hydrogen detection at the likes of Bock, for example, where they're manufacturing hydrogen on a large scale, currently in the grey hydrogen process. And of course, it emits water as a byproduct of its combustion. This is why we're interested in it for the energy transition. It removes that CO2 emission. And actually, when we look at the flame detection later, that's a large part of what allows us to detect those flames in the infrared. So we're just going to whiz through methane by comparison. Again, it's lighter than air. Density of, oh, I was right, 0.7 by comparison to air. I think a little bit less than what I said. It is also an explosive gas, LEL of 4.4% volume in air, 0.4% volume in air, upper explosive limit. As I mentioned, it's also odorless. We've got the ignition energy there, an order of magnitude higher. Methane is not considered toxic, and neither is hydrogen. But generally, as a gas, is extremely well understood. So, we've been dealing with it for decades in these large volumes. And I think that's the main change, really, where hydrogen is concerned. That's typically been used as a feedstock to make other things. It's been used in smaller process systems, small bore tubing. We haven't maybe seen what we're expecting to see, which is large volumes of it stored under very high pressure or extremely low temperatures if we're going to look at liquid hydrogen, and we've not seen the volumes moving through pipework and potentially that hasn't been designed to carry hydrogen originally if we're going to look to reuse assets because that's more efficient. So there's just a lot of changes by comparison to methane. So this is a bit of a table, but I'm just going to pick out some of the key areas here. You can see the flame speed there, which is significantly higher than the other gases or explosive molecules around it. The flammability limits, actually the lowest here is propane, 2.1% volume in air. So although hydrogen is lower than methane, it's not the lowest that we're typically used to dealing with, or even necessarily storing in our homes or our garages, where we have propane gas canisters and things like that. And important to note here is that although the boiling point of hydrogen is extremely low, minus 253 degrees C, which makes it very much a cryogenic fuel if you're going to liquefy it, a lot of learnings can be taken from LNG. So LNG carriers and LNG tankers, bunkering facilities are also operating extremely cold temperatures, not as cold. So really the challenge is going to be to prevent the dispersion of transmission of heat. And that's going to be done using, vacuum and maybe improving the efficiency of the processes that we have already in place, because at those low temperatures, it's extremely hard to keep it down there. But, it's not an absolute unknown. So we're going to move right into hydrogen detection methodology. So it can be a very challenging gas to detect for a number of reasons. The first thing is that hydrogen has no dipole moment, which means that IR detection is not possible. What we mean by dipole moment is essentially it's the electronegativity of the molecule. So when you think of methane, you've got a carbon atom of 4 hydrogen atoms that work to make up the fill out the covalent ring with the electrons on the outside and make a stable molecule. But the sharing of the electrons is unequal, because you've got this very large atom in the middle of the carbon having a lot more protons and a lot more electrons, and you've got these very light atoms on the outside making up the bonds. And essentially what that means is that the pull towards the carbon is stronger, and that we can influence that when we introduce energy to a molecule. Essentially, whenever you use infrared light, what you're looking to do is send out a beam of photons and have those photons interact with the molecule in some way. And that imbalance in the way that the electrons are shared between the atoms really, really helps that. Conversely, when we think of hydrogen, which is H2, and you can also apply this to O2 and N2, oxygen and nitrogen, the molecules are perfectly balanced. It's the same size of nucleus, for each atom, and across both molecules. So it's O2, N2, H2, and that means that the energy just won't be absorbed by the molecule. So we can fire IR at it all day long, but the molecule essentially won't react. They actually do say that a molecule, if it doesn't absorb energy, it will reflect energy equally well. So that can also be used, and there is an example of this later, but it's not necessarily the most useful. So what that means is essentially we've removed this visual detection ability using infrared. This is something that was developed, I guess, in the wake of disasters like Piper Alpha. Historically, they've relied on catalytic bead sensors to look for explosive gas accumulations. Those sensors aren't necessarily able to tell you if they are able to detect gas. They're not fail-safe. There are some caveats to that, which we will go into, but infrared detection is able to tell you that it is unable to detect gas. So it can tell you that it's got beam block, or it's got dirty optics or something like that, and so it can give you that warning. However, catalytic bead can't do that, and because we can't use infrared for hydrogen, that has an impact. The other impact is the fact that there's now no open paths or large area gas detection monitoring for hydrogen when we think about optical methods. Yet, I guess you could add that on the end. So acoustic is the next option here. Again, this is a detection methodology that's been around for a long time. It's listening to for the sound of a leak outside of the range of human hearing. It can cover large areas. Traditionally, it's not been favoured necessarily by oil and gas. Of course, they have line of sight, so they don't need it so much for that large area coverage, but it does react extremely quickly, and we'll go into a bit more detail about that and why. But you have to set the device up properly in order to be able to mitigate against false alarms. If you don't set the right delay time, you don't set the right noise thresholds, it can be susceptible to false alarms. And this is why many systems don't like to use it as part of their executive action function. They rather just use it for monitoring. However, with hydrogen, because you've lost the optical monitoring methods, you have to start to look at other things and other ways. And we'll talk as well about how acoustic can be extremely helpful, specific to hydrogen, later on. And so what we really have to rely on here is point detection. And what we, if you're not familiar with gas detection, the easiest way to think about that is smell as a human being. So if there's a smell, let's say 10 meters away from me, I won't smell it until the gas is diffused sufficiently to reach me. And of course, as it diffuses, the smell gets weaker and weaker. That's essentially the same as a gas detector. And we have to think about this with hydrogen, because as I mentioned, it diffuses so much within air because of that low viscosity that although the detectors can detect it, actually you might struggle to get it up to the explosive concentrations that will set off your gas detection system to alert you that you've got a leak, which can be good and which can be bad. But the good thing is if it's not reaching a potentially explosive concentration, the risk of an explosion is much less. However, you can have undisclosed leaks that could potentially cause issues in other ways. And we also then have this risk of potential small spontaneous ignition, very small jet fires and things like that, because of that small, very low ignition energy of hydrogen. In some circumstances, even the static electricity built up by the flow of its own molecules through a leak can create sufficient energy in order to ignite. And I have spoken to engineers who've worked on these grey hydrogen plants, been on night shift, and said, yeah, I've wandered around the plant and I can just see these little fires going off everywhere. If there's a very small jet fire, of course, it means that it's burning off the gas immediately and you're not getting an explosive gas cloud buildup. However, if there has been explosive gas cloud buildup or a certain amount of gas release prior to igniting, then you now have an explosive gas cloud and an ignition source present. So these are just things potentially to be aware of. Obviously, we don't go into plant design at Dräger, but there are plenty of webinars out there for people who do. So this is some of the leak sources that we can see from hydrogen plants. Of course, the data is quite light because there's not that many plants out there. They're not in huge volumes. This is from the Centre of Hydrogen Safety Conference. And you can see at the bottom here that leaking connections, valve malfunctions, which is stems really, valve stems, and leaks are the largest cause of leaks in a process system, which I'm sure will come as a shock to no one, because when we look at the main reasons for hydrocarbon releases from the 2008 study by the HSE, you can see here in terms of major release, piping again is the main source of releases for major releases. And actually the significant releases here is even more telling because it matches up almost exactly. And this is what we would expect to see. You wouldn't expect to see it to change massively with hydrogen, especially given the fact that if there is a potential leak source, it will leak more readily and more volume will get out as well. But we're seeing hydrogen replicating exactly what we've been seeing over the years for methane as well. Oh, actually, did I have a link to that report? Just go back a slide. No, I haven't. I thought I had. What I can do before I send the presentation out is just pop a link in so that when you click on this, it can take you to that report, should you wish. Right, let's skip on. So this is the point detection that we're talking about here. This is our catalytic bead sensor from Dräger, and essentially this will screw into a number of different transmitters. You can have aluminium, you can have stainless steel, you can have GRP. We do a very high temperature catalytic bead sensor as well, which will go up to 150 degrees C. One of the uses that we've seen for this is potentially within modules containing fuel cells, where essentially the module itself operates at a very high temperature, but they're not wanting to see any loss of containment from sort of the process pipe work inside in and of itself. And so we can potentially put these devices in that high temperature environment. But for very high temperatures, what we would probably do is look to put in a sample system which extracts a sample from the area to be monitored, and we run it over a sensor in an environment that's more conducive to the sensor, a little bit lower temperature, a little bit lower pressure. However, with all sample systems, what that does introduce is a delay time. So I think one of the things that you'll find is key throughout all of the material that I'm going to present here is that there's no perfect solution. There's no silver bullet. You've always got to think about, I can do this with this, but it's not going to work in this application, or I need to do this, but my mitigating factor is this. You know, it's response time, it's temperature, it's what have you. So as we've mentioned, there's no bonds in hydrogen which can absorb infrared energy, which means that we have to go back to the catalytic bead sensor. But Dräger have not rested on our laurels, and we have continued to develop this sensor. So we've improved the ceramics that we use for the pellister sensor inside, and we've also significantly improved the device's ability to resist temperature and pressure and humidity conditions as well. Am I going to say why? I am getting what I put in here. So you can see here, now this is not to scale model. This aperture in the middle here is actually key, but it's much, much smaller. It's a very small pinhole aperture between both the reference and the measurement catalytic bead sensor on the inside. What that allows the device to do is, as pressure, weather, humidity conditions change quite slowly, it allows those to equalize between the two chambers. But should we get, the light's gone out. Right, okay. should we get gas coming in present and a build-up, whether it's slow or fast speed, the aperture is so small that the gas is not going to build up on the measurement side at anywhere near the same rate. It's absolutely tiny, and because even a slow gas release for hydrogen is going to increase at a speed that's much faster usually than the weather conditions, the changing weather conditions, which often take several hours. What we have is much greater stability from our catalytic bead sensors. We've had an offshore operator, I won't say who, change out our from a competitor device to our device after we gave them a device for a free trial. They were having an absolute nightmare with the weather conditions. This was in one of their battery rooms, actually, which is another traditional hydrogen application. And yeah, they saw a huge improvement just from that one device that we gave them to trial, and then they've just switched out all of their devices to the Dräger device. So we have continued to develop. The other thing I will go back and say, so you'll see this kind of flame arrestor mesh, essentially, is what it is. We use this instead of a sintered disc because it's much less likely to get clogged up with any impurities that might be there in the plant. So it just improves the sensor life, but you are still going to need to response check and calibrate these devices on it'll kind of depend on what you set on your interval for your plant, but generally people say 6 months or 12 months interval for these, because you need to check that you've got some response. Of course, with catalytic bead, there's the old problem that if you get certain substances that can coat the catalytic bead sensor, therefore the sensor is unable, as I mentioned, to tell you that it's not in direct contact with the atmosphere and therefore can't detect gas. That is why you need to do a response check on these devices, because you need to check that the sensitivity of the sensor is not being depleted by potential contaminants. However, if you don't have any of those contaminants present, things like H2S, which is obviously present in methane quite readily, but I wouldn't expect it to see it in, for example, a green hydrogen plant where you're performing the electrolysis of water, or silicon, silicates and things like that in the air. If you haven't got those on the site, then your risk of contamination is greatly reduced. One new thing that we have brought out as well with Dräger, we've always had this electrochemical sensor as an ability to detect gas at low concentrations for hydrogen. So this can detect down to, or up to, actually, I should probably say, 3,000 ppm traditionally. That's the maximum that our electrochemical sensor has been able to detect. Do I have that down here? Yes, I do. And the way an electrochemical sensor works is essentially it's like a battery, but it's got one missing component in order to generate a voltage, or a current, sorry. And that one missing component is its target gas. So as soon as the gas comes into contact with the electrolyte, a chemical reaction occurs, which essentially stimulates a current. And the more molecules are present, the more chemical reactions we get, therefore the greater the current. And that is how we measure the concentration, by measuring the electrical current within the sensor. Now, we have recently brought out, and it's so new that it's not actually on our system that I've extracted this screenshot from, where we can do 100% LEL with an electrochemical sensor, which removes the issues around potential contamination or undisclosed failure, really, actually, is what it removes, because an electrochemical sensor, we do check and test that the device is still able to detect gas. The device will do that itself, and we can give that information back into the system. However, as I mentioned, there's no perfect gas detector. So one of the problems with electrochemical sensors is that you can get cross-sensitivity between devices. So again, you still need to be aware of the other molecules that are present in your process that could potentially cause I say what we would determine potentially as a false positive within your gas detector. So that's something that you need to be aware of, because if anything contains something that is cross-sensitive with that electrochemical sensor, it will react. It's a chemical reaction. So oftentimes with gas detection, we're kind of limited by chemistry and physics. We'll do what we can, but we are a little bit limited. Yeah, so those are the ranges of detection. Like I said, top is 3,000 ppm. Now, the percentage volume LEL sensor, 4% volume in air, is equivalent to 40,000 ppm. So what we've done, where we've got this 100% LEL electrochemical sensor, is we've had to change the electrolyte in order to be able to detect that. But we have done that. It's currently in testing in Europe somewhere, I think Austria. And we are going to hopefully be releasing that to the market as another option for the detection of hydrogen. Hydrogen line of sight. Why am I even going to bother talking about this when I've already said you can't do it? We've gone through the dipole moment thing. You can read that at your leisure. In theory, lasers can detect hydrogen. So lasers don't exist in nature. Essentially, it's we have to create a false pattern of light where the wavelengths all move in unison, and we can create it at very, very specific wavelengths. This is where it is different than infrared. So with infrared, we have a light source and then we put a filter on it, and the filter will get us down to a certain amount of accuracy. So for open path gas detection for methane, it is, I never remember which way around it is. It's 2.1 and 2.3 micrometers. One of those is the reference and one of them is the measurement. I think the measurement's 2.1, but I can't be sure. For the point detection, actually, we use infrared at 3.34 micrometers for methane and 3.4 micrometers for propane. That's because we're doing it over a shorter wavelength, so we can use a slightly different, a shorter distance, so we can use a slightly different wavelength. For lasers, you can get accuracy much, much, much greater than what you can get with a filter on a traditional infrared source. So as an example, this is the laser absorption for methane. You can see, yeah, we cover everywhere from 2.1 to 2.4 really in there. And essentially that it's quite a wide band. So each of those little ones is an individual peak that you can create with a laser. Whereas with an infrared device, you're looking at band absorption. So the filter can't get down to those individual peaks. We have to kind of look at a window essentially. Now, I want you to look and pay attention to the scale here at the bottom. This is in micrometers, 2.1 to 2.4 is where we're interested in. I'm going to go here onto absorption lines for hydrogen, which is here, this yellow one, right? Now look at the scale. We haven't even left 2.12 here. So if you imagine this scale is like a laptop screen essentially for hydrogen, and what we're looking at now, the scale that I showed you before would stretch from one end of the car park of your building to the other side of the building. You know, it's just a completely different scale. So that is how accurate and how tiny the peak needs to be in order to be able to detect hydrogen with a laser. You can do it. We are taking delivery, I think, well, maybe we have taken delivery in our research and development department of laser-based hydrogen detection, which is used in spectroscopy, but it's over a very small distance. And what our challenge is to see if we can make that small distance a useful distance over a large area. It remains to be seen. But Dräger are looking at it. So as with the electrochemical sensor for hydrogen detection, you know, we are definitely looking at the challenges that are going to exist and how we can plug those holes. We're definitely not resting on our laurels, but we will be limited, as we always are, by physics, chemistry, and economics. And that leads me quite nicely onto this. So if you recall where I mentioned that hydrogen doesn't absorb energy from infrared, but because it doesn't absorb, conversely, it will reflect. This is this experiment done at the Fraunhofer Institute. I do have the report for this as well, which I can share afterwards. Remind me to include that. This is where they've used laser. Instead of looking for that extremely small absorption line, you can use a laser and reflect the energy back off the molecule, and it will do that very readily. And essentially then what they do is they look for that reflection point using Raman spectroscopy, and they can tell. Conversely, with traditional open path, you can only tell if you've got if you've got a large low concentration gas cloud or a small high concentration gas cloud. It's just counting the number of photons that have been lost by gas interrupting the beam of light. With this, because it's not, there's no absorption, there's actually reflection, they could tell, and it's mentioned in the report, that the location of the gas potentially within that beam path length because it's being reflected. However, because you'd think that that would be a silver bullet, this was done in lab conditions. It doesn't take, they know where all of the other light sources are that are going to potentially throw out light that's going to be picked up by the sensors, and it takes account, it's probably a very clean environment, so minimal dust and things like that. As soon as you put this kind of thing into an external environment, there's going to be far too much interference from the likes of sunlight, other moving light sources that can't be kind of mapped and tracked, dust, dirt. So although potentially this is another way of doing it, it's extremely expensive in theory. Dräger sort of did an initial analysis on this, and we're looking at potentially £100,000 to £200,000 per pair. And whilst I'd love to be able to sell a device at that price, I highly doubt it. And also then we have these issues of contamination as well. That's a little bit more of an extract from the report, which you can read later. Now, hydrogen blends is something that we have to think about as well, because this is probably going to be a stepping stone, something that's going to assist with the commercial viability of hydrogen as an industry, is whereby we can reduce the CO2 emissions of our existing energy system by injecting hydrogen in. And there's been a number of trials done. We were involved with trials, was it called High Deploy down at Keele University? This is where they did some of the first trials with domestic boilers and looking at blending into hydrogen into natural gas pipelines. They started off at 2% and they got up as far as 20% before the introduction of hydrogen started to change the efficacy of the burn and cause issues. So this is kind of generally accepted that you can do up to 20% hydrogen with minimal or no modification to your existing system if it's designed and built to burn methane instead. There are the likes of Siemens, who have built, large power generator gas turbines for power on plants. They say that they can do up to 38% hydrogen without it starting to change the efficacy of the burn. So again, depending on the different plant, you could have a different blend of hydrogen depending what it's able to take. But this does have an impact for gas detection, mainly because of what we talked about and the fact that infrared is blind to hydrogen. So this is an extract from a study by Northern Gas Networks. I link that as well. Maybe it's on the next page. So they did a study on blending. That should be 38% hydrogen and 62% natural gas, where they were looking at the impact on the gas detection system. So, of course, the majority of the gas within the process remains hydrocarbon. So you can detect hydrocarbons with infrared and you can still continue to use those devices. But the point here is important. To account for the lower volume of CH4, we recommend lowering the alarm set points. This is to account for the fact that that infrared device is blind to 38% of that process. So there's an explosive gas cloud leak potentially that's 100% explosive, but that infrared device can only see 62% of it. So you want to reduce your alarm set points by a percentage according to the blend of hydrogen. If it's 20 and 80, if it's 40 and 60, you want to be reducing your set points according to the blend, according to the amount of hydrogen present in the system that infrared device is unable to see. But you can still use, because the majority of the process is going to be methane, you can still use infrared. What I don't have information on, and what I would love to have information on, is at that higher pressure where you have hydrogen more ready to leak, is do you need to reduce your alarm set points even further? So even if you had a 20-80 blend of hydrogen, at high pressure, do you get sufficient hydrogen released above methane that actually reducing your alarm set point by 20%, for example, to account for the hydrogen wouldn't be enough, and you would need to reduce it by 25, 30, I don't know. That would be some research that would be very helpful to have. I will try and link that one as well, or at least send the document out. So this is from the report. Again, you can read this at your leisure, but we're going to go onto a graph shortly, and the points, what A, B, C, and E is, and D is, A, B, C, and E are catalytic bead devices. D is an infrared device. So when we go onto the graph, this will make a lot more sense. So you can see here, this is the visual indication of the infrared device being unable to see the concentration of CO2 as we increase the concentration in the blend as it goes up. In fact, catalytic bead detectors remain largely unaffected and are actually slightly more sensitive to methane than they are hydrogen. So you actually get a slightly safer response here. So if you are looking at introducing a blend of hydrogen into your system and you currently rely wholly on infrared detection, you'll need to reduce your alarm set points accordingly. But you could also benefit from the addition of catalytic bead sensors as well, which are able to see 100% of the process. Acoustic detection. So this is something that we've mentioned. This is probably better when we're thinking more about 100% hydrogen again. And this is really good because it's listening for the noise of a leak. And it can do it over quite a large area. So depending on the pressure, and this isn't linear as well. So for example, a lot of these hydrogen filling stations are operating now at 700 bar. A gas detector on a system that's operating at say 800 bar is not going to be able to detect at a distance 4 times greater than a hydrogen system operating at 200 bar. It's not linear like that, unfortunately. But you will, the higher the pressure, generally, the greater the noise, and you will get some excess distance. Opposite to that is if there isn't enough pressure, then we don't get any sonic speed, and so we don't get enough noise, and so this device becomes ineffective. Really, you need above 4 bar. With hydrogen, because it's such a small molecule and because of its viscosity, it reaches sonic speeds really easily. So it's actually got a really good noise profile. And what you can see here is that you don't want to be foregoing gas detection, just thinking, oh, well, I'm just going to use acoustic then. You need to use a variety, what we call a matrix of detection technologies when you're looking at hydrogen. So because it diffuses so quickly, because it's so influenced by weather conditions, and because a lot of the standards recommend that hydrogen process plants should be put outside wherever possible to prevent that accumulation of gas. These devices are really, really good for determining when you've got a leak, when potentially a catalytic bead point detector isn't going to be necessarily in exactly the right place. You're not going to get the whole concentration build up to reach your alarm set point. You might want to consider using more sensitive hydrogen point detectors as a result, or reducing your alarm set points over that of what we would typically see for methane, say 20 and 40. You might consider 10 and 20 for hydrogen, just because you want to avoid that undisclosed leak as well. That's something that ultrasonic gas detection is going to be really useful for, is not only, okay, we've got potentially outside less of a safety risk because we're not going to get that explosive gas accumulation, but we're possibly going to have undisclosed leaks, which means that all that energy that you spent electrolyzing water, all the energy and money that you spent compressing it and moving it, and all the rest of it could be going up, literally frittering away into the air because you've got a leak that you're not aware of. And UGLD can be really, really good for that. Generally, I'd say we can cover sort of 20, 25 meters. It can go up from there if your pressure is higher. But like I say, it's not linear. So acoustic gas detectors, for those not familiar, is listening outside of the human hearing range. So if you walk onto a plant and think, oh God, this is really loud, how is this going to hear anything? It's not listening to what you're listening to. It's listening to the sound of a pinhole leak. Now, there can be other noises on the plant that replicate that are what we would call safe leaks or expected leaks. I cover that actually. No, I don't. Right, I'll talk about it here. So pneumatic actuators, for example, as you get the piston lifting off the seat of the actuator, right at the beginning of that, you will get it mimicking the behavior of a leak, process leak in your pipeline. And then as the piston moves further off the seat, you'll start to move into the human hearing range, which is what you can hear when a pneumatic actuator activates. What you need to do with acoustic gas detection really is set a delay time, which means that you avoid sort of those friendly leaks or friendly noises triggering the device. Now, of course, an ultrasonic gas detector reacts really, really fast. Lots of research in the methane kind of industries has shown that it can take several minutes actually for methane to build up into an accumulation that is sufficient to trigger the gas detector. For hydrogen, that's even longer, whereas this device can react at the speed of sound. And I know I've said, you know, it can react at the speed of sound, but we need to set a delay. Rule of thumb is around about 6 seconds delay. It will very much depend on your plant, and we would recommend doing a noise survey, which has some considerations to take into account. But 6 seconds is still extremely quick by comparison to the length of time it could take for a gas accumulation to occur that would be sufficient to trigger a catalytic bead device, for example, that might be looking at 25% LEL, which is 1% volume in air. This is where UGLD really comes into its own. So you can see, as we talked about here, the fast response right at the beginning here. This is where you will start to get that device going into alarm. If you've not got it forming executive actions, you'll need someone in the control room that's going to see and notice that. Conventional gas detector response is right down here where we need a vapor cloud to form either toxic or flammable, depends what your gas detection is, and it needs to achieve significant concentration before that device will go into alarm. But what we can see is that this device is actually able to respond even before you get that potential jet fire that we've talked about because of the low ignition energy of hydrogen. So the limitations of UGLD, it's not gas specific. As I've mentioned, not all gas releases are unsafe. You're going to have pressure relief valves and things like that. So we need to set up that false alarm immunity. That requires you to do a sound survey, which will take a general recording of the background ultrasound noise of your plant, things like pumps, compressors, and what have you. We'll need to set that above that, and then you'll need to set a delay time for all of those kind of friendly fires, as it were, when it comes to leaks for this device. And that delay time will depend on your site, but like we say here, rule of thumb, 6 seconds-ish. It also has a sensor self-test here. So this is a piezo microphone that we have in our device, which can also be, what happens is when the noise activates it, the vibration creates a very small electrical current, and then we can measure that electrical current. Similarly, if we apply power to the microphone, it can generate its own noise. So we can do a sensor self-test with this device very regularly, which can confirm repeatedly whether the device is working or not. And so it does reduce the amount of maintenance required. It's very good in outdoor applications, as I mentioned. You don't need to wait for an accumulation, and we do get a very fast response, delay time allowing. As I've mentioned, it does depend on the pressure, and actually this device is looking at leak rate rather than a gas accumulation. So it really does need to know a leak rate, so you'll need to have that figure defined for your process. And as I've mentioned as well, if you've got a low leak rate, you're going to have a shorter detection range. A high leak rate is going to give you a greater detection range, and that will depend on the pressure. Finally, we move on to flame detection. So what we're used to normally is flames that are visible to the human eye. This is because they have a carbon content in them, and they give off, a certain amount of soot and particles, and these emit light, and we can see them. So most flames will give off visible, infrared, and ultraviolet, but with hydrogen, we lose that visible element of it. And what that means is practically that the hydrogen fire here is almost invisible, apart from when you are in at nighttime or in a dark environment. And actually, some of the yellow that you'll be able to see there is essentially the heat of the hydrogen fire burning particulates, dust, and things that are already present in the air. You can see a methane fire actually gives off less visible light than an N-heptane fire as well. N-heptane is a standard pan fire at which we certify all of our devices. So for hydrocarbon fires, actually what we're looking for is the CO2 spike at 4.2 micrometers or 4.3. That's what we're looking for. We're looking for CO2 as a byproduct of combustion. With hydrogen fires, it's quite similar actually, but what we're looking for instead is water as a byproduct of combustion here. So the peak is at 4.3, sorry, micrometers. As you'll know, water interacts with infrared really well. This is why sometimes we have problems with things like condensation and fog when it comes to infrared gas detection. But we use that to our advantage when it comes to hydrogen flame detection, sorry, because that's the byproduct of combustion and we can detect it really well. It's got a good signature. So the flames are also odorless, as well as invisible, and well as giving off very little radiant heat. And again, that's due to the lack of carbon content. So there's just really, we can't smell water vapor, essentially. So it really is important to make sure that you're using the correct form of flame detection for this device. I think I've gone through this. Yes, it emits water as a byproduct of no CO2. So you can use UV-IR detectors for this. UV has a very fast response. You don't want to be using just single UV detectors, to be honest, because they're very, very susceptible to false alarms. That is why the oil and gas industry moved away from them a very long time ago. But when you supplement UV and IR together, it can be effective. But actually what we prefer to suggest is that, again, because IIIR has in recent years become the dominant form of detection for methane, we can do the same for hydrogen. And we just look for those 3 peaks in relation to the water vapor. And essentially, we're looking for the 3 peaks to be met by the reaction of infrared with water at this peak here. This is the Flame 1750. We've just released this. This is our IIIR flame detector. If you're familiar with our portfolio, you'll notice that it looks very similar than all of our other flame detectors, but I can assure you it is different. It's got the different filters on it. And actually, you can use this to detect methane as well at the same time. So methane has water as a byproduct of its combustion as well. So if you are looking at putting hydrogen and methane together in terms of blending, or you are working on a plant that is looking at the steam methane reforming of methane to produce hydrogen, so you're likely to have both flammable substances present, methane does produce water as a byproduct of its combustion. And so you can use this device to detect both hydrogen and methane. The difference is this device can detect at 40 meters range, and that is a sensible amount. A lot of manufacturers will have high sensitivity and low sensitivity and medium sensitivity, and their high sensitivity will say 80 meters detection range, but you can't put it up at that high sensitivity because it gets triggered by fluorescent jackets and reflective clothing and things like that. So be wary of data sheets because those kind of peak figures on the data sheet won't necessarily be available to you as what you can use on the plant. We try and use sensible figures. This is a sensible figure that you can use. For methane, this detector can detect methane fire at a distance of 30 meters. So 40 for hydrogen, 30 for methane. By comparison, our standard IIIR flame detector for hydrocarbon fires can detect methane at a distance of 60 meters because it's looking for carbon dioxide. There's more carbon dioxide. It has a better reaction in terms of the infrared emissions, and so we get a greater distance. So if you're just dealing with methane, you'd still want to use a methane flame detector. But if you have both, you can instead look for the water byproduct emissions for hydrogen or methane fires. And I think, oh no, that's not the end. You'll be aware of this. So ATEX. UKEX, UKCA marking has been postponed, I think, indefinitely. So ATEX still applies, but all of our devices are certified to 2C as standard. But you will start to see that for hydrogen applications, you'll need 2C, or 2B plus H2 can also be accepted for devices, but you can't use 2B devices in a hydrogen plant. I don't think I've got time to go through this. This is an alternative detection method. We've actually looked at this device. It's very, very promising. It works on the basis of specific energy density. Essentially, every gas can take a certain amount of energy, which is specific to that gas, to increase the temperature by 1 degree. That's how this device works. Hydrogen has its own, and it can be used to detect. The problem with this device is it's not SIL rated, and it also does not comply to EN 60079 because of its drift. It mathematically calculates out drift. So with a fast hydrogen release, it will detect it. But if you have a slow creeping weep of hydrogen, there's the potential that it can calculate that increase in accumulation of hydrogen out as drift. That's why it doesn't comply to EN 6007929-1. And so it can't be used as part of a safety system. It can only be used as monitoring. So just be aware of that. This technology has been taken on by Crocon. We did evaluate it and decide not to take it in for that reason, because it's quite expensive just to be able to be used for monitoring. But it's very promising as a promising gas detector. You know, we're keeping our eye on this technology, because if it can change the way it calculates drift, this could be really, really promising. But at the moment, it is quite slow, and it doesn't comply to the regulations for a safety system. That is the end. I think I've got 3 minutes. No.